In this screencast, we're going to work on a couple of half-life problems. We're going to do it two different ways. One's for the table, and for the table, we look at the amount over time elapsed. We look at all the half-lives. And the other way is, I guess, the algebra way, which is this equation right here. So for problem number one, we're looking at starting at 100 grams. And we start at time 0. That's our initial. And then after a half-life happens, which is half-life is 24,000, that's what's going to go down here. Half-life happens, this many years passes, 24,100, and we'll have half of 100 grams, which is 50 grams. And we'll do it again for the next half-life, which will be an additional 24,100 years, which brings us to 48,200 years. And then half of 50 is 25 grams. And that doesn't quite get us to 96,000, so we have some ways to go. And so another 24,000 years. Just keep adding the 24,000 years. And that gets us to 72,300. And that gets us down from 25, so divide by 2. That gets us down to 12.5, which is not what we are going for yet. And then down here we go down to the 96,400. And then we divide by 2 here, and that gets us to 6.25. And so we kept going until our year matches how many years went past. And our answer matches the answer key given to us, 625 grams. So we went through one half-life and then another, then another, then another, until we hit 96,400 years. And of this original 100-gram sample, there's only going to be 6.25 grams left. The other way is to use this equation here, where the becomes a bit more of a plug and chug type math. The amount remaining, A, equals the initial amount, which is this 100 grams, times a half raised to the n power, where n is the time, which is 96,400, divided by the half-life, which is 24,100. That reduces down to 5. Four. Glad I typed that in my calculator. 4. And so 1/2 to the 4th. Oops. Is 100 times 0.0625. And that gets us to the answer as well. Check. So there's no one way better than the other. The equation will let you deal with years and masses that don't fall precisely on the half-life. But if you do fall precisely on the half-life, then this table works for you. For one of the latter questions, instead of being told the half-life, you can be given the half-life. And again, you could do the algebra way or you could do the table way. Both involve a little bit of thought, or at least the table way involves a bit more thought. When you have still have the amount, and still have time elapsed. And here we have the sample contains 4 milligrams, 4.0 mg. That's at time 0. What is, let's see, the sample contains 1 after that many years. So half of 4 is 2, half of 2 is 1 milligram, and it tells us the years here, 8.92 times 10 to the 9th, so billions of years, which takes quite some time. The issue is, what is the half-life? So how did I go from here to here and then here to here? And what's that half-life there? Kind of looking back at the equation, if you think about the exponent to the n power, so here's the equation is a equals initial 1/2 to the n power. This is focusing kind of on the n, where the n equals the time, n being how many half-lives there are, n being the time passed, 8.92 times 10 to the 9th divided by the half-life, t 1/2. And so since it took 1 half-life and 2 half-lives, I know that n equals 2, so I can solve for the half-life. And that would give me t 1/2 equals 4.46 times 10 to the 9th years. So you can do it algebraically this way, just really focusing on the n. You can plug in numbers as well, or you can just focus just on the n. If you kind of use the table method, you'll get how many half-lives there are, and you can solve for n directly. You can use the equation where a is the amount, which is after the half-lives happen, which is 1 milligram, equals the initial amount, which is 4 milligrams. And again, you can just kind of solve for the half-life. You can solve for 892 times 10 to the 9th divided by the half-lives. So that takes some algebra to solve for x, and depending if you're in algebra 1 or algebra 2, you might not even be able to solve for x. But if you can, great. Use your log rules. Otherwise, do the table and just go right after the letter n. I hope that helps. One other key feature is, or I guess another question was about how to deal with the 15/16ths. All you would do for that one is start with the amount. So when you have amount here, this is the time. Doesn't matter how much you start with, you can just start with a 1, and then half of that, and then half of that, half of a half is a quarter, half of a quarter is an eighth, half of an eighth is a 16th. And so how long will it take for 15/16ths to decay, meaning you have 1/16th remaining. And so now you can just kind of plug in these numbers here. You have the half-life as being 1599. So you always start at year 0 and then just 1599, and then keep going from there. 1599, 3198, 4597, and then 6396, which is what the answer is. Number 5. Okay. I hope that helps. Keep practicing. Thank you.